Hello there. Welcome to this video on duration and convexity of bonds. These two measures are useful in the risk management of portfolios of bonds. We'll discuss the basics, the methods of calculation, and the uses of the two measures. So let's get going. Suppose you have invested in several US Treasury bonds of different maturities. You believe that the US Fed will reduce the relevant interest rate by 50 basis points in the next policy meeting and reduce the rates further over the next few quarters. You know that if the rate is reduced, the yields of the bonds will go down and the yields will change by an increase in the prices of the treasury bonds of different maturities because the price of a bond is inversely related to the changes in the interest rates. If the interest rate rises, the bond price falls, and if the interest rate decreases, the bond price increases. This is true for most bonds. This inverse relation is obvious for the discounted cash flow model used for calculating the price of a bond. According to the model, the cash flows from the bond are discounted at the required yield, usually the YTM, to get the present values of the cash flows. The sum of the present values of the cash flows is the price of the bond. The sum of the present values of the cash flows is the price of the bond, which is also called the intrinsic value of the bond. The formula is as follows. The present value of a bond, or its intrinsic value P, is equal to present value of the interest payments plus the present value of the principal repayment. That is, P is equal to C1 divided by 1 plus Y plus C2 divided by 1 plus Y raised to the power 2 and so on till Cn divided by 1 plus Y raised to the power n and M divided by 1 plus Y raised to the power n, where P is the present value of the bond today and Ct is the coupon payments for the period T moves from 1 to n, and M is the maturity value of the bond, n is the number of years to maturity, and Y is the required rate of return, usually taken as the yield to maturity. Therefore, as the YTM, which is the yield, in the denominator increases, the value of the bond will decrease, and vice versa. Note that by increase in Y, we mean that the Y becomes more positive or less negative. The question is, by how much will the bond price change if Y changes by 1%? Let's take a quick look at the following bond. This bond has 5 years to maturity. The face value is $100. The annual coupon is 8%, which is $8, and the yield to maturity annual is 10%. If we calculate the price of the bond, the intrinsic value, using the discounted cash flow model, we have to take the present value of all the cash flows and sum them up. For example, at the end of period 1, the cash flow of $8 is discounted by 1 plus 10% raised to the power 1, which is 1.1, and the present value of the cash flow at the end of year 1 is $7.27. At the end of year 2, the cash flow is discounted by 1 plus 10% raised to the power 2, and the present value of the cash flow is $6.61, and so on. At the end of year 5, you have the $100 principal repayment plus the $8 coupon, which is discounted by 1 plus 10% raised to the power 5. The present value of the cash flow at the end of year 5 comes to $67.06. If we total all the present values, we get a bond price of $92.42. Now suppose the YTM changes from 10% to 9%. All the other factors remain the same. The present values of the cash flows will increase because the denominator has decreased, and the sum of the present values comes to $96.11. Therefore, for this bond, as the yield falls from 10% to 9%, the bond price, which is the sum of the present values of its cash flows, increases from $92.42 to $96.11, which is a rise of approximately $3.69. In percentage terms, the rise is $96.11 minus $92.42 divided by $92.42, which is equal to approximately 3.995%. As we will see later, this 3.995% figure is approximately the combined effect of the modified duration and the convexity of the bond. Also note that the magnitude of change for a bond will depend upon various factors such as its period to maturity, the annual coupon, and of course the YTM. When we hold all other factors such as periods to maturity and the annual coupon constant and change the YTM, the change in bond price can be calculated using the modified duration and convexity. Therefore, if you know the modified duration and the convexity of the bonds in your portfolio, you can mathematically predict the change in the value of your bond portfolio for changes in YTM. The two measures help investors in risk management of fixed income portfolios. If you know the possible impact of the change in interest rates of the value of the fixed income instruments that you own, you may tweak your portfolio to optimize the impact. By tweaking, we mean selling some existing bonds and buying more of some bonds in your portfolio so that the net impact of the change in YTM is nearly zero. You can also use futures to counter the impact of the changes in interest rates. Basically, you must be mindful of the varying interest rate sensitivities of the prices of the bonds that you own and know the duration and the convexity of your bond portfolio. And you must take corrective action based on the expected changes in interest rates. If you can do so successfully, you can bulletproof or immunize your bond portfolio to the changes in interest rates. You'll be able to stabilize the value of your portfolio to a great degree. So let's first discuss the duration measure. When we talk of duration, we usually talk of two measures, the Macaulay's duration and the modified duration. We need to first calculate the Macaulay's duration. The modified duration is easily derived from Macaulay's duration. The Macaulay's duration measures the average maturity of a bond's expected cash flows. Macaulay's duration is measured in years. The average maturity in years tells you what the effective maturity of the bond is based on its intrinsic value and the expected cash flows received at various points in time. Essentially, Macaulay's duration is the weighted average of time in years to receive the expected cash flows from the bond. Macaulay's duration gives you the weighted average time that an investor must hold the bond so that the sum of the present values of all the expected cash flows is equal to the intrinsic value of the bond. The expected cash flows include the coupons and the par or the maturity value of the bond. We'll discuss this soon when we understand the calculations. Macaulay's duration and consequently the modified duration, which is the price sensitivity of a bond, is impacted by its coupon rate, yield, and the time remaining to maturity. If we hold the other factors constant, duration is lower for bonds with higher coupons, higher yields, and shorter maturities. The formula for Macaulay's duration is as follows. D is equal to the summation of Ct divided by 1 plus Ytm raised to the power t divided by P into T, where T is equal to 1 to N. Ct is the cash flow at time T. P is the price of the bond based on the discounted cash flow model or the intrinsic value of the bond, and N is the number of coupon payments. This term, Ct divided by 1 plus Ytm raised to the power t divided by P, is called the weight. Modified duration is simply D, which is the Macaulay's duration, divided by 1 plus Ytm. Modified duration is the first derivative of the price with yield. It is a partial derivative because numerous factors impact the duration or the price of the bond, but only one factor, the Ytm, is used to calculate the derivative. Let's take an example to understand the calculations for modified duration and Macaulay's duration. We take an 8% coupon, $100 face value bond with 5 years to maturity. The current YTM is 10%, which is greater than the coupon rate of 8%. The cash flows that an investor can expect from the bond are $8 coupon at the end of year 1, year 2, year 3, year 4, and year 5, and the $100 maturity value at the end of year 5. Here, $108 is the coupon plus maturity value cash flows at the end of year 5. Using the discounted cash flow model, we can calculate the price of a bond by discounting the coupons and the maturity amount with the Ytm to calculate the present values of the cash flows and totaling the present values. As we can see, the discounted amounts are $7.27, $6.61, $6.01, $5.46, and $67.06. When we total all these present values, the bond price comes to $92.42. It is easy to see the inverse relation between bond price and the yield relative to the coupon rate. If the yield is greater than the coupon, the bond price is below the par value. Had the yield been less than the coupon, the bond price would have been above the par value. Let's first look at the term Ct divided by 1 plus Ytm raised to the power t. This term in the Macaulay's duration formula is basically the present value of the various cash flows in this column, where the PVs are divided by P, that is CT divided by 1 plus YTM raised to the power T is divided by P. The resultant figure is the ratio of the PV to the discounted cash flow price or the intrinsic value of the bond. That is, what proportion of the price is the cash flow. This term, CT divided by 1 plus YTM raised to the power T divided by P, is the weight assigned to the time period in years. Obviously, the final cash flow of interest plus maturity value has the highest proportion of the bond price. As evident, the cash flow is in dollars. The present value of the cash flows is also in dollars, and the weight is unitless because we divide dollars with dollars. Now, when we multiply the weight with time in years in this column, we get figures that are in years. When we total these figures, we get Macaulay's duration in years. To be clear, why is it called weighted maturity of the bond? For this bond, D is equal to 1 into $7.27 plus 2 into $6.61 plus 3 into $6.01 plus 4 into $5.46 plus 5 into $67.06. And this sum is divided by $7.27 plus $6.61 plus $6.01 plus $5.46 plus $67.06. This is basically the intrinsic value of the bond. The numerator is the weighted sum of the time periods, the weights being the present value of the cash flows. Therefore, the numerator is the summation of the time period into present value of the cash flows. The denominator is the summation of the weights, that is the sum of the present values of the cash flows, that is the price of the bond or the intrinsic value of the bond. To get the modified duration, we divide D, which is the Macaulay's duration, with the term 1 plus YTM. Again, the resultant figure is in years because we divide the Macaulay's duration in years with a number. For our bond, modified duration is equal to 4.281 years divided by 1 plus 10%. The denominator is 1.1. Therefore, the modified duration is 3.892 years. So what do these numbers mean? How do we interpret the calculated duration figures? Macaulay's duration is the weighted average maturity of the bond. It gives the time the investor must hold the bond to recover the price paid for the bond. In the case of our bond, the investor must hold the bond for 4.281 years to recover the bond price calculated based on the discounted cash flow model. The modified duration measures the expected change in the intrinsic value of a bond immediately after there is a 1% change in the yield to maturity. The YTM can change because of factors such as changes in the benchmark rates. The intrinsic value includes the accrued interest, although only the clean price, which is the one without the accrued interest, changes when the YTM changes. The accrued interest is obviously based on the promised coupon, which is calculated based on the face value. The change in the bond price is equal to minus modified duration into the change in the yield to maturity. The minus sign indicates the inverse relationship between the bond price and the change in yield. For example, if the YTM increases, the percentage change in the YTM will be a positive number. Therefore, the change in the bond price will be negative. That is, the bond price will fall, and vice versa. For our bond, if the YTM increases by 1% from 10% to 11%, then the bond's price will fall by around 3.892%. That is, the bond price should move from $92.42 to $92.42 into 1 minus 3.892%, which is equal to $88.82. Note that the duration will change as the YTM changes. Therefore, this figure of 3.892% is correct only for changes from 10% to 11%. That is, the bond price should fall to $88.82. So let's confirm this. As we see, the new bond price based on the 11% YTM is $88.91, not $88.82. The bond price has fallen less than what we expected purely based on the modified duration. As we will see later, the difference is largely because of the convexity concept. Duration is a linear measure of the change in bond price with yield to maturity. This basically means that duration wrongly tells us that the change in bond price remains constant as yields increase or decrease. Mathematically, however, it is seen that the relation between bond price and YTM is not linear. The graph is a curve, usually a convex to the origin. More on this later. Also note that the modified duration indicates that the investor will need to hold the bond for 3.892 years to get compensated for the loss due to the decrease in bond price. The compensation will come in the form of the profit in coupons that are reinvested. Let's take an example of another bond. We keep the coupon and the YTM same. We only change the number of periods or the maturity of the bond. The maturity is now 3 years instead of 5 years. The face value remains at $100. Annual coupon is 8% or $8, and the YTM is 10%. As we see, with a shorter maturity, all else being equal, the duration decreases as the time to maturity falls from 5 years to 3 years. This is obvious because the bond price will be recovered faster because of the shorter maturity. Also note that the face value does not impact the duration because the cash flows and consequently the bond price based on the discounted cash flow model changes based on the face value. Therefore, the weights will not change. For example, if the face value is changed to $200, the cash flows, the present value of the cash flows and the bond price change, but the duration doesn't change because we are weighting the period with the proportion of the cash flow to the bond price. Here, the face value has been changed to $200 and the duration, the Macaulay's duration and the modified duration, they remain the same. Note that if the coupon is increased from 8% to 10%, all else being equal, the duration decreases because the bond price will be recovered faster because of larger cash flows. As we can see, the duration falls from 4.281 years to 4.170 years, that is the Macaulay duration, and the modified duration falls from 3.892 years to 3.791 years. And what happens if there are no coupons at all? That is, it is a zero coupon bond. As we can see, the Macaulay's duration is the same as the time to maturity because there is only one cash flow which receives 100% weighting, which is the maturity value at the end of the bond's life, that is in the 6th year in this particular case. For a zero coupon bond with a different maturity, say 10 years, all else remaining the same as the above zero coupon bond, we can see that the Macaulay's duration increases to 10 years. Now, if we keep this 10-year bond and simply change the YTM and the face value, the Macaulay's duration will not change. But the modified duration will obviously change because of the change in the YTM. This is because the decrease in YTM will cause the modified duration to increase. Because the formula for the modified duration is Macaulay's duration divided by 1 plus YTM, and as the YTM changes, the Macaulay's duration divided by 1 plus YTM will change. Let's discuss the importance of duration in fixed income management by revisiting some main points that we have learned so far. Macaulay's duration tells the effective average maturity of a fixed income portfolio. The measure can help a portfolio manager to protect or immunize his portfolio from changes in interest rates. The modified duration estimates the interest rate sensitivity of a portfolio. The higher the modified duration, the more sensitive to yield the bond price, or the bond price is more volatile when the yield changes. Basically, higher duration indicates higher interest rate risk for the bond. The face value does not impact the duration of a zero coupon bond or any other bond for that matter. The modified duration for all bonds is less than the Macaulay's duration for positive interest rates. For bonds of same maturity, a bond with a higher coupon rate will have a lower duration because the higher coupon payments during the initial period will help decrease the weighted average time in years to receive the expected cash flows from a bond. The cash flows will be recovered faster. For bonds with the same coupon, a bond with the higher time to maturity will normally have a higher duration. This is obvious as the weighted average of time in years to receive the expected cash flows from a bond will increase as there will be more coupon payments. All else being equal, as the YTM increases, both the duration measures, the Macaulay duration and the modified duration, will decrease. This is also obvious from the formula because the cash flows are discounted at a higher rate, leading to lower duration. For zero coupon bonds, the Macaulay's duration is the same as the time to maturity because there are no coupons. There is only one cash flow, that is the face value upon maturity. That cash flow has 100% weight. For deep discount bonds, the duration may reduce when the maturity increases, all else being equal. For a perpetuity where the maturity is infinite, the duration is 1 plus YTM divided by YTM. For a 7% YTM, the duration will be 1.07 divided by 0.07, which is 15.28. The duration is only impacted by the YTM. For a perpetuity, the present value weighted cash flow in the first few years makes up most of the duration value. Note that the duration is not a 100% accurate measure. We need to factor the convexity to accurately predict the price sensitivity of a bond. So let's discuss the convexity of a bond. As we saw in our example, the modified duration is unable to predict the change of a bond price with a change in yield with 100% accuracy. The problem is that while duration is a linear measure, the actual relationship between the change in bond price and the change in YTM is a curve instead of a straight line. The curve is convex to the origin, except in certain cases such as callable bonds and mortgage-based securities. Duration changes with yield, and if the relationship is linear, at some point the bond price will become zero. That's impossible if the company remains solvent. And this is actually not the case because of convexity of the bonds. As we noted earlier, duration is different for different YTMs, all else being equal. The change in duration with YTM is measured by convexity. That is, the convexity measures the rate of change of duration or the slope of the curve. Therefore, the convexity of a bond at any point on the yield curve measures the rate of change in duration as the YTM changes. Let's discuss how convexity is calculated. We will discuss its meaning and implications in more details thereafter. Basically, you take the second derivative of the bond price with the yield to maturity by taking the duration calculations a bit further. The formula for convexity is T into T plus 1 star weight divided by 1 plus YTM square. As we know that the weight is equal to Ct divided by 1 plus YTM raised to the power T divided by P. Weight is the ratio of the present value of cash flow to the bond's intrinsic value as calculated based on the discounted cash flow model. As we know, the bond price is a summation of the present values of the cash flows. There are some methods of calculating convexity which are different from the one we'll discuss, but we'll use only the above formula for our calculations. For our 5-year bond, we multiply the figures in the weight star T column, that is weight into T column, with T plus 1 and divide by 1 plus YTM whole square. Then we add the resultant figures to get the convexity. For our 5-year bond, the modified duration is 3.993 and the convexity is 21.0465. This convexity figure is the adjustment that we need to make according to the following formula for correcting the error in estimation if we predict the bond price change purely based on modified duration. Now the change in bond price is equal to the impact of duration plus the impact of convexity. Therefore, if we predict the change in bond price purely based on duration, we will not arrive at an accurate figure. The formula for the change in bond price is minus modified duration into change in yield. This is basically the duration effect which we have calculated earlier, plus 0.5 into convexity into the change in yield whole square. That is, delta P is equal to minus modified duration to delta YTM into 1 by 2 into convexity into delta YTM whole square. The convexity impacts the change in bond price. The convexity impact adjusts the change in price predicted by the modified duration to reflect the actual relation between delta P and delta YTM. Basically, the convexity of a bond is added to its duration according to the above formula to arrive at a relatively more accurate measure of the price sensitivity of the bond. The convexity corrects the duration by adding or subtracting based on the above formula so that the convex relation between bond price and changes in the YTM is captured. Note that the convexity itself cannot help you predict the magnitude of change in a bond's price with the change in YTM. You need both the modified duration and the convexity to predict the price change. For example, for the following bond, the relation between YTM and bond price is a convex curve, not a straight line. The figures have simply been calculated using the discounted cash flow model for valuing the bond. The blue curve shows the actual changes in bond price with changes in yield. The orange line is drawn to show the bond price with change in the yield relationship as predicted by the modified duration. Note that the modified duration orange line is just an approximation drawn to show the difference between the actual price change and that predicted by the modified duration. The difference is this area and this area. The actual change in bond price can be predicted using the previously discussed formula. Delta P is equal to minus modified duration into delta YTM plus 1 by 2 into convexity into delta YTM whole square. Let's take an example to understand this. The modified duration of our bond is 3.993 and the convexity is 21.0465. These values are true for the 5-year bond with annual coupon of 8% at the YTM of 8%. If any of these parameters change, the duration and the convexity will change. The duration will increase as the YTM decreases, and same goes for convexity. So based on these figures, we can accurately predict the change in bond price when the yield moves from 8% to 9% or it falls from 8% to 7%. Let's use the formula first to calculate the price change when the yield moves up from 8% to 9%. Based on the formula, delta P is equal to minus 3.993 into 9% minus 8% plus 0.5 into 21.0465 into 9% minus 8% whole square. We arrive at a figure of minus 3.8875%. That is, when the yield moves up, the bond price falls by 3.8875%. Therefore, the bond price should fall from $100 to $100 into 1 minus 3.8875%, which is equal to $96.11 approximately. Therefore, the convexity adjustment helps us correctly capture the true relationship between change in bond price and the change in yield. Also note that, as mentioned earlier, as the yield changes, the duration and convexity also change. For an increase in yield, as in our case, the duration and convexity declined. Therefore, if you want to predict the price change from 9% to 10%, you need to take the base bond price as $96.11 instead of $100 and the duration at 3.942 years and the convexity at 20.5654. Coming back to the change in YTM from 8% to 9%, had we calculated purely based on the modified duration, we would have got a figure of delta P is equal to minus modified duration into YTM, which is minus 3.993%. The revised bond price would have been accurately estimated at $96.007, which is arrived at $100 into 1 minus 3.993%. Therefore, the modified duration measure would have overestimated the fall in bond price with a 1% increase in yield. Let's now calculate the change in bond price if the yield falls from 8% to 7%. As you know the formula, delta P is equal to minus modified duration into delta YTM plus 1 by 2 into convexity into delta YTM whole square, which is equal to plus 4.10% approximately. Therefore, the revised bond price will be 100 into 1 plus 4.10%, which is $104.10. The figure matches with the figure calculated based on the discounted cash flow model. However, you must note that if you take several places of decimal, the figures may not match 100%. However, with the convexity adjustment, you are much closer to the truth than solely based on the modified duration measure. In our case, the modified duration measure would have predicted a 3.993% increase in the bond price instead of the 4.10% actual rise. Therefore, the modified duration measure underestimates the increase in price of the bond when the YTM falls. Therefore, convexity is a friend of the investor. For small changes in interest rates, the difference between the change predicted by the duration and the actual change is small. The difference increases non-linearly when the yield changes are large. Therefore, modified duration is definitely not suitable for large changes in YTM. For large changes, the difference between the actual and the modified duration predicted change increases. If we see the price yield graph again, the shape of the graph is called positive convexity. This region here shows the underestimation in the increase in price when the yields fall. For example, if the yield falls from 6% to 4%, the price actually increases up to this point, whereas the increase predicted by modified duration is less. up to this point. The price rise is underestimated by modified duration. On the other hand, when the yield rises from 10% to 12%, the modified duration overestimates the fall in bond price. In fact, the price falls by a lesser amount as compared to that predicted by modified duration alone. For bonds with positive convexity, the price rises more than predicted by the modified duration when the yield falls, and the price falls less than predicted by modified duration when the yield rises. As we know, convexity measures the rate of change of duration. The duration of positively convex bonds increases as the YTM falls, and the duration declines as the YTM increases. In effect, the price increase when the yield falls by X% will be more than the fall in price when the yield increases by the same amount. This is a good news for investors because you will benefit more when the yields fall and lose less when the yields rise. All else being equal, a bond with a higher convexity will have a higher price than a lower convexity bond. Higher convexity bonds should be preferred by investors. With negative convexity, the curve is shown in this graph. The amount of price appreciation is less than the amount of price depreciation for a particular interest rate change. The bond's duration increases as the YTM increases. Callable bonds and mortgage-based securities have negative convexity. Now, one valid question is, why should we go for such cumbersome calculations for duration and convexity and then use the delta P is equal to minus modified duration into YTM plus 1 by 2 into convexity into YTM square, delta YTM square formula, if we simply can use the discounted cash flow model to calculate the expected bond price at different yields to maturity? Why should we do all this instead of directly calculating through the discounted cash flow model? The answer is that you can and you should do so if you have only a few bonds in the portfolio. There is no need to calculate duration and convexity and apply the above formula for calculating the expected bond price when the YTM changes. However, if you have hundreds of bonds in your portfolio, it is more efficient to calculate the duration of the portfolio and predict the change in the bond portfolio value as the yield to maturity changes. The duration of a portfolio of bonds is equal to the weighted average duration of the bonds in the portfolio, where the weighting is done by the amount invested. For example, suppose you have two bonds in your portfolio with durations of 5 years and 10 years respectively. You have invested $400,000 in the first bond and $300,000 in the second bond. The duration of your portfolio of bonds, the two bonds, will be the weighted duration of your two bonds as follows: $400,000 into 5 years plus $300,000 into 10 years divided by $400,000 plus $300,000, which comes to 7.143 years approximately. Convexity is directly related to the coupon rate and the bond's remaining term to maturity. The lower the coupon, the higher the convexity. Zero coupon bonds have the highest convexity. Lower coupon rates translate into lower yields, which in turn result in higher degrees of convexity. Of course, this holds when all else is held constant. What are the practical implications? If a portfolio manager believes that the interest rates will fall and therefore the bond prices will rise, he should attempt to tweak the bond portfolio so that the portfolio's duration increases. This is because the more the duration, the higher the sensitivity of the bond to the changes in interest rates, and convexity lends a helping hand to the investor. On the flip side, if the interest rates are likely to rise and therefore the bond prices are expected to fall, the portfolio manager should try to reduce the duration of the portfolio. This is because the bonds with shorter duration and shorter maturity will be less impacted by the increase in interest rate as compared to those with higher duration. As the duration is decreased, the portfolio will become less sensitive to interest rate changes. Again, convexity lends a helping hand to the investor. In an increasing interest rate scenario, one should prefer bonds with shorter duration, as the fall in bond prices will be less as compared to that of higher sensitivity bonds. On the other hand, if the interest rates are expected to fall, bonds with higher durations should be preferred. The duration of a portfolio can be decreased by increasing the weight of the lower duration bonds, for example by buying bonds with lesser duration or selling bonds with higher duration. Similarly, portfolio duration can be increased by increasing the weight of higher duration bonds, that is by buying bonds with higher duration or selling bonds with lower duration. Another way to look at it is that the interest rate rise, bonds with higher duration will experience greater fall than the lower duration. Those with higher convexity will fall slowly, that is at a lower rate. If the interest rates fall, bonds with larger duration will rise more as they are more sensitive as compared to bonds with lower duration. Those with higher convexity will rise faster at a faster rate. Therefore, investors should prefer bonds of higher convexity, all else being equal. Note that one can easily understand these implications from the formula for change in the price of a bond, which is delta P is equal to minus modified duration into delta YTM plus 1 by 2 into convexity into delta YTM whole square. Let's take the case of positive convexity and an increase in YTM. If the YTM increases, delta YTM is positive. Therefore, the first term on the RHS, which is basically the modified duration impact, which is equal to minus modified duration into delta YTM, will be negative. We are multiplying a negative number with a positive number, so the result will be negative. The second term will always be positive if convexity is positive. This is because the square of any number is positive. Therefore, delta YTM square will always be positive. If delta YTM is positive, the convexity impact will be positive because the convexity is positive. Hence, delta P will become less negative because we are adding a positive number, the convexity impact, to a negative number, which is the duration impact. This means that delta P will be less negative than that predicted by modified duration alone. Therefore, the bond price will actually fall less than that predicted by the modified duration alone. Positive convexity reduces the fall in the price at that point in the curve for an increase in the YTM. Let's take the case of positive convexity and a decrease in YTM, that is the yield falls. If the YTM decreases, delta YTM will be negative. Therefore, the first term on the RHS, the duration impact, which is equal to minus modified duration into delta YTM, will be positive. We are multiplying a negative number with a negative number, so we'll get a positive number. The second term will always be positive if the convexity is positive. This we have discussed earlier. This is because the square of any number is positive. Therefore, delta YTM whole square will always be positive even if delta YTM is negative. Therefore, if delta YTM is negative, the convexity impact will be positive if, of course, the convexity is positive. Hence, delta P will become more positive because we are adding a positive number, the convexity impact, to a positive number, the duration impact. This means that delta P will be more positive than that predicted by modified duration alone. Therefore, the bond price will actually rise more than that predicted by the modified duration alone. Positive convexity increases the price of a bond at that point in the curve for a decrease in the YTM. The impact of convexity will be quite the opposite if the convexity is negative. Negative convexity and increase in YTM case will be quite different. Now, if the YTM increases, delta YTM is positive. Therefore, the first term on the RHS, that is minus modified duration into YTM, will be negative. The second term will always be negative if the convexity is negative. This is because the square of any number is positive. Therefore, delta YTM square will always be positive. If delta YTM is positive, the convexity impact will be negative for negative convexity. Hence, delta P will become more negative because we are adding a negative number, the convexity impact, to a negative number, the duration impact. This means that delta P will be more negative than that predicted by modified duration alone. Therefore, the bond price will actually fall more than that predicted by modified duration alone. Negative convexity increases the fall in price at that point in the curve if the YTM increases. Let's take the case of negative convexity and decrease in YTM. If the YTM decreases, delta YTM will be negative. Therefore, the first term on the RHS, that is minus modified duration into delta YTM, will be positive. The second term will always be negative if the convexity is negative. This is because the square of any positive number is positive. The square of any negative number is also positive. Therefore, delta YTM square will always be positive. So, if delta YTM is negative, the convexity impact will be negative for negative convexity. Hence, delta P will become less positive because we are adding a negative number, the convexity impact, to a positive number, the duration impact. This means that delta P will be less positive than that predicted by modified duration alone. Therefore, the bond price will actually rise less than that predicted by modified duration alone. Negative convexity decreases the increase in price of the bond at that point in the curve for a decrease in YTM. Similarly, if you see the duration and convexity formulas carefully, you can understand why, for example, duration and convexity decrease with an increase in YTM. Here we end our discussion on duration and convexity measure of bonds. Please like this video and subscribe to our channel to support us. If you have any questions or comments, please write in the comment section or email us at wiseatfinance@gmail.com. Thanks for